Bernoulli's law for incompressible flow. According to Bernoulli, the pressure of a fluid is a constant. In practice, let's say a fluid is flowing through a pipe with wide and narrow boundaries. The same amount will be flowing across the entire pipe, as we mentioned in the continuity law. In wider boundaries, a large quantity flows slower, so we have a higher static pressure because the fluid is more stagnant, it's more static, it's pressing against, the boundary, so to speak, the axial boundary, the skin. You have higher static pressure, lower dynamic pressure. But in narrow boundaries, the same amount will flow quicker, increasing the dynamic pressure. So what actually happens is that the dynamic pressure Q would be higher. However, you would have a lower static pressure, so it would press with a lesser force against the skin of the pipe, for instance. Okay, but in all cases, the pressure remains constant. That's the point. What we're talking about is a constant pressure throughout a pipe system. Okay, now, so the entire pressure values remain constant. So P plus Q plus rho GH is equal to a constant. Now, the pressure of the fluid against like the pressure generated from a specific height would be negligible. Why? Because throughout the pipe, there's no differential of pressure between, the middle of the pipe and the bottom versus another point where you have a narrower section of the pipe. Okay, it's not like such a high distance. This rho GH is usually an important factor when you have a leak. Okay, but within a pipe, it doesn't actually influence the overall pressure. Okay, so it is negligible. What you have is the pressure, not because of height, the pressure of the fluid pressing against the skin of a pipe or a tail section, a wing section, okay, plus the dynamic pressure that is due to motion. So this entire sum, okay, without the rho GH, remains constant, with P is the static pressure equal to force divided by area, plus Q is the dynamic pressure is equal to 1/2 rho V squared. So rho GH, which is the potential energy with H representing the elevation, is negligible. It's not considered in most cases because the elevation is almost the same throughout the flow path, being subject to very tiny changes, so it doesn't affect the flow itself. All right, so we don't account for it. A physics explanation at the molecular level: higher speeds increase Reynolds number, leading to a more turbulent flow while reducing the viscosity, because Reynolds number is equal to rho VL divided by mu, so it is directly proportional to velocity of the fluid and inversely proportional to the viscosity. So higher speeds increase the Reynolds number, so they dominate over the viscosity, which is the inner force pulling air molecules together for an airplane, for example, but it's the same concept for liquids. So the fluid molecules are pulled away from each other in this case, and because of this high speed, since the viscosity is lower, the fluid would press less against the surface of the wing, let's say a hydro wing for a submarine. This would be resulting in having a lower static pressure versus a higher dynamic pressure. Remember that the pressure is always constant, so if one pressure goes up, the other pressure factor goes down so as to keep the pressure constant throughout the path of the flow. All right, so higher dynamic pressure because of higher velocity means lower static pressure. Now, for lower speeds, Reynolds number, which is proportional to the fluid velocity, decreases the shear stress. Okay, so you have a lower Reynolds number, it decreases the shear stress pressure vector parallel to the flow, so it becomes more viscous, which becomes weaker than the inner force pulling the fluid molecules together, all right, and attracting them to the flow surface. So it leads to a more laminar flow where the streamlines remain close to the flow surface. In aerodynamics, this translates into a flow following the curvature of the wing. Now, but for even lower Reynolds number, what we're talking about is the static pressure becomes higher than the dynamic pressure. All right? So you might get to a point where you're no longer producing lift. Okay? But the static pressure becomes higher and the dynamic pressure lower. So this is how they change. Let's talk a little bit about Poiseuille's law. So this law describes the laminar flow through a cylindrical pipe, and it quantifies how the flow rate depends on the fluid's properties and pipe geometry. So Q, which is the volumetric flow in meter cube per second, so how much volume is traversing a cross section within a second, is equal to pi R4, R is the radius of the pipe in meters, to the power of 4, times delta P, which is the pressure difference between the two ends of the pipe, divided by 8 mu L, L being the length of the pipe. Here we notice immediately how the flow rate is inversely proportional to the length. So as much as you have length within the pipe, that would kill the flow rate. Okay, that would like slow down the flow of the liquid. Meanwhile, when you have a differentiated pressure between the first end and the second end, this differential of pressure would increase. When you have a high difference of pressure, this would increase the flow rate, and of course you have the radius of the pipe that would also influence the flow rate. For a larger radius, you would have a much higher flow. Submarine lift underwater. Imagine a submarine fin or tail section underwater. How does it generate lift to climb from a specific depth to a more shallow one? From a very deep point to a more shallow, which is a closer point to the surface. At first, despite the fact that Bernoulli's equations and the concept of lift and drag apply almost the same for both air and water, however, when it comes to water, it is nearly incompressible. So there's no significant change in temperature caused by the flow. Thus, the density is not changed and neither is the pressure. As for the viscosity of water, it is higher than that of the air. And this makes water more prone, more susceptible to flow separation. So it is more sensitive to having its boundary layer, which is the layer of the flow that is close to the surface skin of the hydrofoil, more prone to be detached from the surface, okay, at high speeds. So flow separation is when the fluid layer close to the surface detaches from it. Okay, usually water having a high viscosity is more prone, more susceptible to, transition from a laminar to turbulent flow. This is what we are referring to exactly. Now let's portray the section of a hydrofoil. By the way, it is the same concept for aerodynamic wings. So what is the anatomy or structure of a hydrofoil? At first, the part that hits the water is called the leading edge. That's the edge that cuts through the water. Then the one behind at the tip is the trailing edge. Between them you have a virtual line which is called the chord line. It is virtual. It is used actually to measure the angle of attack, or which is the angle between this chord line and the flow direction of the water. You also have the upper part of the wing, or the hydro wing in this case, is called the upper camber, and the lower part, which is beneath the chord line, is called the lower camber. The fluid flows from the leading edge to the trailing edge in two directions, one above the foil called the upper camber, and one below the foil, which is through the lower camber, or by scraping the lower camber. The chord line is an imaginary line, again, connecting the leading to the trailing edge, used to measure the angle called angle of attack between the flow path and that chord line. Going back to Bernoulli's equation, the pressure is always constant from above or below, from either above or below the tail section or the wing section, hydrofoil in such case. In other words, and based on the law of continuity, the mass linear momentum is constant. The linear momentum is constant from above and below the hydro wing. So in other words, the water flowing from above and that from below should arrive together at the trailing edge at the same time. So the water hitting the leading edge, either flowing around the upper camber or the lower camber, in both directions, the same water points that were at the same alignment, at the same line, so to speak, should arrive at the same time at the tipping edge of the, the wing section, which is the trailing edge. However, the water traveling on the upper camber is following a curvature, a long path, so to speak, much longer than the water flowing from below, which is around the lower camber. The lower camber, as you see, is more flat. So the distance traveled by the same molecules of water from beneath the lower camber is much shorter than the one traveled by the ones, going around the upper camber. Since they need to arrive at the same point or at the same time to the trailing edge, this means that the ones that are flowing around the upper camber should travel faster. So in other words, to make it short, the dynamic pressure on the upper camber of the wing would be much higher. In result, as a consequence, since we have a pressure constant, the static pressure on the upper camber would be lower than that on the lower camber. The static pressure here would be lower, okay? Would be much less, less intense than the static pressure below the wing or at the lower camber. So the differential of the static pressure would make the water from below push harder than the water from above. The water at the lower camber push harder than the water flowing above on the upper camber, which would lead to a push, which we call lift. This will generate the lift for the hydro wing. So let's read it along. The camber, is more flat on the lower, the lower part of the wing. So it needs, the molecules above need to travel faster than the molecules below. This is what you need to take away. So the dynamic pressure from above increases versus a decreasing static pressure. Why? High velocity means lower static pressure, okay? So thus the dynamic pressure increases, okay? So, and since we have an overall pressure constant, when you have a smaller static pressure or a higher dynamic pressure, you have a smaller static pressure, okay? And you can even visually notice it because, the molecules of water are nearly scraping, they are not even scraping the surface. They are much distant from the surface of the hydrofoil compared to the molecules of water that are flowing from beneath, okay? So you have a higher static pressure from beneath, which will produce lift. Again, as a result of the high velocity for the fluid moving around the upper camber, the static pressure on the top of the foil becomes lower than that under the foil or against the lower camber due to water traveling slower. Of course, in aerodynamics, that would be air. Hence, the differential of pressure, which is P under, being greater than P over, P here, the pressure here is greater than the pressure over the wing. This pushes the submarine upwards and helps it to climb, creating lift. Rho GH is negligible since its reference level is the wing itself. All right, and again, as a reminder, static pressure F over A plus dynamic pressure 1/2 rho V squared plus rho GH negligible is equal to constant. Another way in which a submarine or any submersible creates lift is through Newton's third law of action versus reaction. So imagine you extend your hand from a moving car window. As you tilt it, actually, if it was still horizontal, you won't feel anything. It will, smoothly cut through the air. But as you tilt it down, it gets in the way of the airflow. As it pushes through the flow, the wind pushes it upward. It means that the wind pushes back against your palm. So it pushes it upward, creating lift. That's the same thing for hydrofoils in water. When you tilt it down, you increase the angle of attack. That's the angle of attack between the chord line and the flow direction, which generates more lift and helps it to go upward. Of course, with lift, you have an induced drag as well, which tilts the lift force vector, okay, backwards. So the resulting vector would become slanted, not vertical, because you have the lift vector and you add it to the drag vector, which is the induced drag among other factors of drag. The induced drag is generated because of lift itself. So the resulting vector would be slanted a little bit backwards. Again, as a reminder, or as a note, as a side note, the lift itself, okay, so it's generated by, on one hand, this Bernoulli equation of the pressure differential and Newton's third law of action versus reaction when you create an angle of attack against water as the hydrofoil moves through water. You need both of them. You see, the law of Bernoulli is not enough to lift a submarine or even an airplane. That's why the airplane drops the flaps in order to take off. Okay? In the same way, you have the hydrofoil, it needs to tilt the angle back in order to travel or climb to a shallower depth. The lift force, of course, any force is expressed in Newton, and based on the concept that we've spoken about previously, you have a direct relationship between the lift and the dynamic pressure. So they are correlated. Actually, they are so dependable, so in a way that they are directly proportional. So what is the relationship between lift and dynamic pressure Q? L equals CL, which is a lift coefficient, depending on the airfoil shape, surface roughness, and Reynolds number. The three of them, contribute to determining the value of CL, times Q, which is the dynamic pressure, 1/2 rho V square. That's the same thing in the equation below, which is an expansion of the upper equation. It's still the lift. So Q is equal to 1/2 rho V square, V being the velocity in this case, times the surface area. So the dynamic pressure, as you multiply it by the surface area of the wing or the hydrofoil in such case, you get times, of course, the lift coefficient, you get the lift force in Newton. Rho is the air density in kilogram per meter cube. V, air velocity, actually it is the water velocity in this case relative to the hydrofoil, but it's the same concept still. S is the wing area, hydro wing, what we're talking about in our scenario, can be expressed as S, surface, or A, area in meters squared. However, and CL is the lift coefficient, which depends on the airfoil shape, surface roughness, and Reynolds number. Drag force, the formula of the drag is very similar to the formula of lift, all right? So very close. Instead of lift, you have the drag force equal to a drag coefficient this time, times Q. So also, you see the correlation between the lift and drag, because when you have lift, you have also the forces of the fluid pushing against the wing or hydrofoil. This also creates drag. So D equal drag coefficient times the Q, which is the dynamic pressure, times the surface of the hydrofoil, equals CD times 1/2 rho V square S. The same concept. Let's do a small example, small exercise. Let's say you have a fluid such as water, around, you know, density 1000 kilograms per meter cubed. The drag coefficient for, not for the fluid, you actually have a sphere going through a fluid, flowing into water, okay? Or rather, the water itself is flowing against the sphere. The drag coefficient for the sphere is 0.47. For the water scenario, rho 1000 kilograms per meter cube. Viscosity of the water is 0.01 poise. And velocity of the water around the sphere as it's drowning is 10 meter per second. By the way, you can say also that the velocity of the sphere itself in the water is 10 meter per second, okay? So it's either the velocity of the sphere going into the water or that of the water flowing around the sphere. The radius is 0.01. Hence, the drag against the metallic sphere as it cuts through the water is the following. And by the way, note that S is the surface of the sphere exposed to the drag, which is half of it. Now, at first, the surface or the area of a sphere from the outside, I'm not talking about the section of a disk within the sphere, but the surface is 4 pi r squared. Now, the area exposed to the water flow where the drag is occurring the most is, we're assuming it is half of the sphere, half of the actual sphere or ball, which is 4 pi r squared divided by 2, okay, equal 2 times pi is 3.1459, around that value, times the radius square. Radius is 0.01 square, so equal to 0.00062,832 meters squared. Okay, so the drag force is equal to drag coefficient times the dynamic pressure, which is 1/2 rho v squared, times S, is equal to 0.47 times 1/2 times 1000 times v squared, which is velocity squared, times 0.00062,832, which is the surface area exposed to the flow, is equal to 14.7655 Newton. Prandtl's theory. Let's talk about Prandtl's theory and induced drag. Starting with Prandtl's theory, according to Prandtl, which is a Germanic, like Deutsch scientist or engineer, elliptic wings are the most ideal for well-distributed circulation, generating lift with minimum induced drag caused by the downwash. Okay, we will talk about what is drag, what is the downwash. Actually, when the wing section or the hydrofoil, if you will, cuts through the water, it is pushing against the water. So the water pushes up, pushes back the wing and generates lift. So it is the action versus reaction, Newton's law. But also, as it flows down against the wing, the hydrofoil, it creates what is called an induced drag caused by the downwash. The downwash means the water flowing down after it pushes the wing up, okay, creates an induced drag. Let's start with the concept of circulation. What is circulation? The circulation, okay, at point y, by the way, it is the sum of all velocity vectors around a foil. That is the circulation. It's the integration of all velocity vectors over a wing section. So gamma y is equal gamma 0, which is the maximum circulation along the wingspan, okay, or the circulation value at the center of the wing. That is the maximum value. Square root 1 minus 2y divided by b. Okay, so 2y, y is the point at which we are measuring the circulation, and b is the wingspan. Wingspan means that's the distance between the two tips of the hydro wing. So let's imagine a plane for an instance. B, or the wingspan, is the distance from one tip of one wing to the other tip at the other side on the opposite wing. Or in other words, visually, it is the width of the airplane. Okay, distance from one tip to the other. This is actually what we call B, or the wing span. Of course, in hydrodynamics, that would become hydro wing or hydrofoil span. So by looking at this equation, we notice how when B goes to plus infinity, okay, which is the wingspan, the squared fraction 2y over b squared becomes 0, and hence gamma y becomes gamma 0. So, or to put it in a different way, the maximum circulation along the wingspan, okay, becomes equal to gamma 0, which is the maximum value at the center, okay, when the wing has an infinite length, an infinite span, which is theoretical, of course, okay? And there are many reasons why you cannot go much bigger on a wing span, because you have the aerodynamic or the fluid dynamic loads against the wingspan. So if you stretch it to a specific length, you might break it due to the pressure and drag, due to adverse pressure that can break it, okay? It becomes more structurally deficient. So the maximum circulation along the wingspan, which is typically the circulation value at the center of the wing, gamma y is equal gamma 0. In practice, you won't have an infinite wingspan B, of course, but the geometry that provides the longest span with an optimum flow and less induced drag is an elliptical wing section, or an elliptical hydro wing section. Aspect ratio. So in the previous slide, we've already addressed the B, which is the wingspan, or the distance between the two tips of the wings, either aero wings, wings of an airplane, or hydrofoils for a submersible. So B again is the distance between the first tip of one wing to the second tip of the next wing, or the width of the submersible, so to speak. Now, aspect ratio is a ratio which is also related to the wingspan. It defines the geometry of the wing. Now, we have two types of wings usually. You have the rectangular simple wings. For that one, it would be, the aspect ratio is the ratio between the wingspan B, or the distance between the two tips of the wings, and the chord line, which is the length of the chord line, or the line connecting the leading edge of the wing to the trailing edge, only in rectangular wings. However, in more complex wings, such the ones that you see here, it is the ratio between the wingspan B and the overall area of the wings. The overall area of the wings, which is S here plus S here. So the entire surface of the two wings, both of them. Again, for rectangular wings, AR, or aspect ratio, is equal to B over C, or wingspan, divided by the chord line length. For generalized wings, AR is equal to B squared, or the wingspan squared, divided by the surface area. Now, if you notice these two equations, in simple terms, long narrow wings are associated with a high aspect ratio, and short and wider wings with a low aspect ratio. Now, these two factors are very important in defining the structural robustness of the hydrofoil, okay, on one hand, and on the other hand, defining how much induced drag you would have, how much lift efficiency. They are very important parameters in these measurements. Aspect ratio impact. You see, the aspect ratio is not a non-intentional measurement. It actually has a purpose behind it, which is, it is an essential factor that determines the hydrodynamic performance of the hydrofoil. Below, we represent the difference between high and low aspect ratio in relationship to different hydrodynamic parameters such as lift and drag. Let's start with high aspect ratio. You see, for high aspect ratio, it means that B is greater than the surface area, or the C for rectangular shaped wings. For high aspect ratio, the wings, of course, would be longer because B is very high, and narrower to get a smaller surface. like the gliders, for instance, for the aerodynamic aspect of things. The same concept for water. So characteristics, it is more efficient for lift, or the lift factor is more efficient, okay? They have a lower induced drag because of the downwash when the water like downwashes through the hydro wing, okay? The induced drag is usually smaller than that for a low aspect ratio, but structurally they are weaker. Why? Because the tips are far from the fuselage, so they are prone to bending. And not only that, but the area of contact between the plane body or the submersible body and the wings. So for example here, okay, the area of contact is relatively high, okay? But for thinner and longer wings, the area of contact would be smaller, which means that they would be more prone to breaking apart, okay? Because when the area of contact with the plane body or the submersible body is smaller, okay, they become more susceptible to aerodynamic or hydrodynamic loads, which can break them apart. They can collapse, okay? So, which is a characteristic of high aspect ratio wings, okay? And they are less compact, so they are stretched apart, okay? And they cannot handle strong hydrodynamic loads. For low aspect ratio, however, which is, by the way, a characteristic for wings in F-16s and jet fighters, where they need to handle a much higher aerodynamic load in such case. Actually, for water applications, you would have a low aspect ratio in general, okay? So they are short and wide wings, just like you see here, e.g. fighter jets. So also the area of contact with the fuselage is much larger, so which enables them, you know, to sustain a strong hydrodynamic load, strong pressure without breaking. And also they feature a better maneuverability, structurally stronger, the tips are closer to the fuselage, reducing the bending and the bending moment, because the distance between the tip and the fuselage is small. Larger area of contact with the fuselage, of course, also giving more strength, more structural strength to these wings or hydro wings. But at the same time, they generate a higher drag, higher induced drag. Why? Because the tips are very short, okay? So the downwash and the wake turbulence is much higher for low aspect ratio wings. Downwash and induced drag. In the previous slide, we kind of floated these two phenomena, these two concepts of downwash and induced drag, but without expanding on them. So let's talk about these two things. And how do they happen? What's the main cause behind them? For the downwash, according to Newton's third law, of course you know that already, for every action there's an opposite and equal reaction. So when the submarine's hydro wing generates lift as it pushes the water down and cuts through the water with high velocity, in its turn, you know, the water, the water flowing down creates a downwash. This is what we call the downwash. But in its motion, it pushes back, okay? It reacts against this hydrofoil motion, creating lift, and generates what is called induced drag. This is different than the drag that comes because of the motion itself. This is another component that adds to that drag. Induced drag means it is caused by the lift itself. It's caused by the action to generate a lift on the hydrofoil. This is why it is induced. So this downward flow of deflected water is called the downwash. This is the downwash. This phenomena is usually more noticeable, more visual or visible or observable behind the wingtips, as it creates vortices, eddies, and twirling spirals you see behind these hydro wings for large boats, for submarines, etc. Induced drag. Now, The other byproduct of lift is what we call the induced drag. In the process of generating lift, the wing deviates the water flow in the downwash. This causes the upward hydrodynamic force not to be perfectly vertical, okay, because of the pushback. So you have another component added to the vectors, which is, to the lift vector, which is the induced drag, okay? So the resultant vector would be slanted backwards because of the induced drag. This means that this vector, which is the red one, okay, is the sum of two forces, of which the vertical lift component and the other, which is the induced drag component that we call, okay, induced drag. So the resulting force is not vertical, it is slanted a little bit backwards. What is the value of the induced drag? So induced drag is given by this equation. Di, or drag induced, is equal to PEQS divided by L square. P or pi is actually, the same pi of circles. E is called the Oswald efficiency factor or lift efficiency factor. It's a value that is between 0 and 1, okay, determined by the type of wing, the type of hydrofoil, its shape, okay. For an ellipsoidal shape, for an elliptical shaped wing, you'd have a more like higher value for lift efficiency than for another type of wings or sectional shapes for wings. You have Q, of course, it is the dynamic pressure. Always the dynamic pressure has to do with the induced drag, the drag and the lift, okay, they are correlated, times S, which is the surface area. So for larger surface, you notice you would have a higher induced drag, but inversely proportional to L square. So for a more efficient lift, you would have a slower or a smaller drag, induced drag value, okay. Again, so di equal P or pi EQS divided by L square. Again, pi is 3.14, you know that. E, the Oswald efficiency factor, a value between 0 and 1. Usually for elliptical wing tips or wing sections, you would have a value so close to 1, okay, because it's the best type of wings. Q is the dynamic pressure, it is equal to 1/2 rho v square, v of course the velocity, S is the surface area, divided by L or the lift force. So for much powerful lift, you would have a smaller induced drag. But notice something here. The induced drag is directly proportional to the surface of the wing. So for larger surfaced wings, okay, or in other words, for lower aspect ratio, you would have a higher induced drag. We've seen that in the previous slide. So Oswald's efficiency factor is a number between 0 and 1. That is a measure of how much can a wing generate lift with less induced drag. That's the factor. One being the idealistic elliptical wing, that is theoretical, actually it doesn't exist, and it allows a perfect flow without any induced drag. Okay, so as a reminder, it is designated as induced due to the fact that it is caused by the lift action. Okay, and again, it is proportional to the surface or inversely proportional to the aspect ratio, because aspect ratio is b squared over divided by the surface. All right. Prentle's theory. So a real wing is a finite model that produces a downwash behind, which alters the effective angle of attack. Okay, not the real angle, the effective angle, like the angle that's actually working at the attack. So this theory is a foundational fluid dynamics and aerodynamic model, essentially, developed by Ludwig Prandtl, German engineer in the early 20th century, pertaining to finite aerodynamic wings. Okay, so the theory relates to the geometric attack angle with the downwash induced angle. You have the geometric attack angle, okay, which is different than the downwash induced angle, and the resulting lift to come up with a consistent distribution. Okay, so it is correlated with circulation. Let's put it this way. Okay, at first, this theory applies when considering a steady, incompressible, and inviscid flow. Inviscid means the viscosity doesn't change. Okay, and a small angle of attack. Also, a thin wing, the case for most commercial aircrafts. Okay, so what is the formula? Alpha y. It means that the actual, okay, the actual angle of attack is different than the geometric angle of attack, which you measure by finding the angle between the flow direction and the chord line. The actual effective angle of attack, okay, that's the one playing out, is equal to the geometric angle of attack minus gamma y, which is the circulation, divided by 4 pi v, that's the velocity, okay? So integrated between minus b divided by 2 plus b divided by 2. These are, you know, the two distances of the wingspan, okay, which is along the wingspan, okay, times 1 divided by y minus y prime, okay, dy prime. All right, so for a longer, actually, yeah, for a higher, either a higher velocity, okay, for a higher velocity, let's say v goes to infinity, the geometric angle, because this entire compound here, this entire component becomes 0, so the effective angle of attack becomes equal to the geometric angle of attack, okay? Or when the circulation is, you know, that circulation ratio becomes, you know, y minus y prime becomes, if you will, infinite, okay? So when this entire component becomes 0, then alpha y becomes alpha geometric. Going back to aspect ratio, AR. Now, by resolving Prandtl's equation, a relationship was established between the induced drag coefficient, not the induced drag, but the coefficient of this induced drag, and the aspect ratio. So with higher aspect ratio, we have less induced drag. This is what we mentioned before, okay? So let's break it down for a visualized airplane model or submersible model, okay? And try to figure out by reasoning whether this submersible or airplane would have a high or low aspect ratio and how it would perform aerodynamically or dynamically in the fluid. Okay, at first, this is what concerns me, you know, this is what interests me the most here. You have the drag coefficient is equal to the lift coefficient square, so they are truly related to each other, divided by 4 pi e, which is the Oswald factor, times the aspect ratio. Again, the aspect ratio is the difference. You see, that's the ratio between the b squared, or the wingspan, divided by the surface area. So for a high aspect ratio, you have less induced drag. For longer wings, you would have a less induced drag, correct? This is what we're talking about mainly in this case, okay? So basically, let's consider, actually in water, you cannot have that, but if we're talking about aerodynamics, for planes with longer wings, you'd have a much more efficient lift with less induced drags. Why? Because the wingtips are very far along, you know, the foil, okay, along this wingspan, okay? So you would have minimal vortices or minimal wakes at the tips of the trailing edge, okay, at the you know, at the tips of the trailing edge and at the tips of the wings. Meanwhile, for smaller wings, you would have a more turbulence, okay, a more turbulence. You would see, like when you're moving the spoon, which is short relatively within coffee, you notice that you have these eddies, these swirls, localized swirls of liquid. These are wakes, these are turbulence, okay? Why? Because the tips are not tall, they are small. This is what produces more wakes, more turbulence, okay? This is the relationship between the aspect ratio and the induced drag. And by the way, yeah, this is an induced drag when you move a spoon within coffee. Let's do an example for Reynolds number. If we recall the other exercise where we found the drag against a metallic sphere of radius 1 centimeter drowning in water. Okay, let's calculate right now the Reynolds number for the flow. So the metallic sphere having a radius of 1 centimeter or 0.01 meters is drowning in water. Rho is equal to 1000 kilograms per meter cube of 20 degrees Celsius. Viscosity is equal to 0.01 Pascal per second. Actually, the real value is 10 to the power minus 3, but let's assume that this value is correct. In this case, with a speed of 10 meters per second. What is Reynolds number? So, RE or Reynolds number is equal to rho VL divided by mu. L is the sphere diameter in this case, or the distance of the flow. We are considering that's the distance of the flow, correct? So Reynolds number is equal to rho VL divided by mu, which is equal to 1000 times 10, which is the velocity, of course, 1000 being the density, times 0.02, which is twice the radius. The diameter is twice the radius, or 2 times 0.01 centimeters, or 0.02 meters, divided by 0.01, which is the viscosity, or 0.01 Pascal per second, equals 20,000. By the way, this value is dimensionless. It means that it does not have any dimension, any international system unit, okay? So RE is around 10 to the power 4, okay? So based on drag coefficient values for a sphere, the drag coefficient is around 0.47, all right? Forces acting over a hydrofoil. Let's consider, for instance, a submarine, like in this illustration. So what are the different forces acting against this submarine? At first, T is the thrust force pushing the submarine forward, usually, of course, generated by the propellers, which is, you know, the system of blades at the rear end of the submarine, not showing here in this illustration. As they push the water backwards, the water propels the submarine forward. That is the conservation of linear momentum. This is also Newton's third law of action versus reaction. You push the water backwards, so the water propels the submarine forward. Then D is the counteracting force against the thrust, which is the drag. Both the one induced by lift, which we've referred to before when rotating or tilting the hydro wings, and the one that is generated by the movement itself as the submarine cuts through the water layers. Then you have L, which is the lift force generated by both the attack angle and the shape of the hydro wing. By the way, in leveled, not flight, in leveled motion, which means when you have you are guarding the same altitude, usually you don't use much of attack angle. You are counting alone on the shape of the hydrofoil, okay, the shape of the hydro wings, which generate enough lift, okay, to counteract the weight of the submarine. Plus you add to that the buoyancy of the fluid, because you see you have a buoyancy which is equal in such case, because given that the submarine is completely submerged underwater, the force of buoyancy is equal to the weight that has been replaced by the submarine. So you get the volume of the submarine, then the mass of that water equivalent to this volume, m equal rho times v, times the gravitational acceleration g, and you get the force of buoyancy. And finally, the final force is the weight of the submarine counteracting both the lift force and the buoyancy, which pushes the submarine downward, okay? So when these forces are equal to each other, you would have a dynamic equilibrium, meaning that the entire submarine would be moving at the same velocity. That is Newton's second law of actually that is Newton's first law of equilibrium, both dynamic and static. Static means it is motionless, okay, it is perhaps on the dock, and dynamic equilibrium, it means that there's no acceleration or accelerated variation, so the velocity is kept the same throughout the motion inside water. Here we're going to talk about Kutta-Joukowski theorem, which is fundamental in fluid dynamics. Why? Because it relates the lift generated by a rotating object, such as propeller, moving through a fluid, to the circulation flow around it. What is circulation? Circulation is simply the integral or sum of all velocity vectors around the hydrofoil, around the wing, okay? These are the velocity field vectors around a closed curve of a hydrofoil, a closed curvature of either a wing for an airplane or a hydrofoil for a submersible in hydrodynamics. This assumes, of course, an inviscid, incompressible, and steady flow conditions. So incompressible means that there's no compression and change of density. The flow is steady, so it is the flow curvatures are fixed, okay, these streamlines, and there's no change of viscosity. This is what inviscid means. And it is derived from the potential flow theory. It applies to the trailing edge. So the lift force is equal to rho times V times gamma. Or in other words, it is equal to the fluid density in kilograms per meter cube, usually 1000 for water, but of course it changes due to the change of the temperature of the water in specific depths, times the velocity of the fluid, velocity of the water around the submarine, times the circulation sum value, which is an integration of velocity vectors around a closed loop times ds, okay, integrated throughout the surface. Now let's talk about another concept, which is the energy head. What is the energy head, or head of pressure, so to speak? By definition, it is a way of expressing different forms of energy, such as pressure, velocity, and even elevation, as their equivalent in potential energy, so to speak, or equivalency value for a fluid height in a column, okay? So what would be like the equivalent of a dynamic pressure in height terms? That would be like 1/2 rho v square is equal to the pressure over a height, which is rho gh, okay? So what is the equivalent height to get the same value for dynamic pressure? This is what we're talking about. We are expressing different types of pressure energies in terms of height or elevation. This is essential for understanding how energy is transferred in flowing fluids, like in Bernoulli's equation. Okay, so you have three types of heads. At first, you have the elevation head, or Z. That is the potential gravitational energy of a fluid because of height, okay? It is the height above a reference level, for example, water reservoir mounted on concrete pylons. That would be the height from the water tank all the way down to the floor, to the ground where the poles are standing. Then pressure head, which is P over gamma. P over gamma, okay, that's the height of fluid that would cause that pressure, where P is the pressure and gamma is rho g. It is the specific weight for the fluid, okay, causing that pressure. So P over gamma is the height of fluid that would cause that pressure. And finally, velocity head, which is V squared divided by 2g, okay? That is the energy due to fluid motion, kinetic energy. So it is very similar to the dynamic pressure, if you will, okay? So where V squared over 2g is the height of a fluid, or the height a fluid needs to fall from in order to reach the V speed. Let me repeat the last expression, the last concept. So velocity head, or V squared over 2g, is the energy due to fluid motion, or kinetic energy, where V squared divided by 2g is the equivalent height of a fluid where the fluid needs to fall from in order to reach that V velocity or V speed. So the total head is the sum of all head values. Total head defined by H is equal to Z, which is elevation head, plus P over gamma, pressure head, which is due to the height of the fluid, or the height of the fluid that would cause that pressure, plus V squared over 2G, which is the height from which the fluid needs to fall in order to reach the V speed or V velocity. To give a practical example, let's say water flows through a pipe from a tank. Okay, at a point you measure elevation. The elevation of the pipe is equal to 5 meters. Pressure P is 50,000 Pascal. Okay, and velocity V is equal 3 meters per second. The fluid density being rho equal 1000 kilograms per meter cubed. Of course, the gravitational acceleration is 9.1 meter per second square on the surface of the Earth. That's the average, actually, because you have a higher gravitational acceleration on the poles where you are closer to the core of the Earth. It's larger than the one near the tropical areas where you have like the sphere is a little bit more compressed and you have a higher distance from the core, from the center of the Earth. So let's convert the pressure to pressure head. At first you have P over gamma for the pressure head, which is 50,000 Pascal, divided by gamma, gamma being rho G, correct? Which is the density 1000 times the gravitational acceleration 9.81 equal 5.1 meters. Second, velocity head, which is V squared divided by 2G. V is 3 meters per second squared divided by 2 times 9.81 equal 9 divided by 1962, around 0.46 meters. Finally, the total head H is equal to Z, elevation, plus P over gamma, pressure head, which is 5.1 here, plus V squared divided by 2G, which is the velocity head, or 0.46 meters. So it is around 10.56 meters. That's the final answer. Fluid flow and boundary layer. Laminar flow versus turbulent flow. So you have two types of flows, as we mentioned, laminar versus turbulent. But at first, what is the boundary layer? What do we define as the boundary layer? Boundary layer is a thin region of fluid close to a flowing surface, i.e. wing, where viscosity has a significant effect, okay? In this layer, depending on the scenario, whether you have laminar or turbulent flow conditions, plus airspeed, density, attack angle, the flow is either laminar or turbulent. So let's talk at first about laminar boundary layer. Laminar boundary layers appear for low speeds, relatively low speeds, and smooth surfaces. We cannot have rough surfaces in order to enable the flow to be curved, perfectly laminar, meaning that it is layered, one layer on top of the other, and there is no turbulence. There is no rotational directions, no rotational trajectories for the particles, okay, of the fluid. So, characteristics: flow is smooth, with ordered layers of fluid flowing on top of each other, with a regular curvature following that of the wing surface. Velocity vectors are smooth and parabolic, increasing gradually from the surface. Drag is lower, the flow is less stable, and is largely affected by disturbances, so it is so easy for the flow to break and to become turbulent. And it can be disturbed easily by ice on the surface or changes in air pressure or water pressure in such case. As for the thickness, it is usually a thinner layer for laminar flow than the turbulent boundary layer. As for turbulent boundary layer, you have this layer appears for higher speeds, rough surfaces. It is chaotic with a higher amount of vortices, swirling motions, eddies, and intermixing in the flow. So you have intermixing between different, what used to be streamlines, intermixing between the fluid particles or molecules, higher drag. That's also another thing that characterizes turbulent flows. You have higher drag, higher skin friction due to irregular vortices and irregular broken air curves. It is more stable, not easily interrupted, and resistant to air low disturbances, okay? And is usually thicker than laminar boundary layers. As a visual for that, if you notice here, okay, this is what turbulent flow looks like. And by the way, this would be the boundary layer. Now this is a laminar flow. As you look at it, the curves are parallel to each other. It is more ordered, not chaotic. And this would be the boundary layer. That layer that has a thickness, by the way, between the curve of the flow and the wing surface, or the hydro wing surface in such case when we are talking about hydrodynamics. As for a reminder for laminar versus turbulent flows, you see for laminar flows you have the curves or the flow directions or lines are parallel to each other, where the maximum flow speed is at the middle, at the center of the flow. And you see there's a stability of velocity of different lines. As for turbulent flows, you have rotational flow, you have vortices, you have an intermixing between different molecules of the fluid, such as in a pipe flow. You see here the u vector, which is the velocity vector, is changing. It's not stable, okay? It's non-uniform, so to speak. And also, again, for the laminar, as you see, the thickness, now here it's not very visible, but the thickness of the boundary layer is very thin, okay? It's very close to the surface of the hydro wing. For turbulent flows, you have a much larger separation between the curvature of the flow and the hydro wing itself. Now let's talk about the values of the velocity when it comes to a laminar flow, velocity vector u, and boundary layer thickness. Okay, so for a laminar profile, the characteristics are u divided by u. By the way, u, y, or u, small u, is the velocity at a distance y from the surface, divided by u, which is the free stream velocity or maximum velocity, is around y, which is the distance, okay, divided by delta, or the boundary layer thickness, to the power of n, where n represents a shape factor or velocity profile characterizing the distribution of velocity around a boundary layer. Okay, so n is around a value from 1.75 to 2, depending on the shape. Okay, you can get it from a chart. Now, as for the boundary layer thickness, it is around 5 times x. X, by the way, is the flat plate length, is the length of the plate, or the length of, you can say, chord line, divided by square root of Reynolds number, okay, in this case. As for turbulent profile characteristics, the velocity u divided by u, again, u is a velocity measured at a distance y from the surface, meaning distance y from the surface skin, okay? So if you go up from the hydro wing, we are trying to measure the velocity of the flow over that wing at a distance y, okay? At a thickness y from the wing, divided by u, which is the free stream velocity, is around y, which is that distance again, divided by the thickness of the boundary layer. By the way, y is greater than delta. Y is at a point, or depending on where we are measuring, but delta is the thickness of the boundary layer. So y is measured in the same direction as delta. It is the thickness from the surface of the hydrofoil to a specific point. So u divided by capital U is around y divided by delta to the power of 1/7. Again, delta is the boundary layer thickness, and y is the point of measurement above the wing, the hydro wing or the aerodynamic wing, depending on the scenario. As for the boundary layer thickness, it is around 0.37 times x, where x is the distance from the wing skin, actually is the cross-sectional distance, the distance of the wing from the trailing to leading edge, divided by square root of Reynolds number to the power of 1/5, where Reynolds number is equal to ux divided by nu, which is the kinematic viscosity. Flow separation. Flow separation happens when the boundary layer adhering to a surface detaches. This is mainly due to adverse pressure gradients overcoming viscosity. Viscosity, it keeps liquid molecules ordered in a streamline and close to the flow surface. This usually happens when the fluid slows down to a point where the streamlines become very weak and are easily broken by adverse pressure. So the adverse pressure pushes against the viscosity on the surface area of a hydrofoil, peeling away this boundary layer. Okay, so the fluid flowing close to the wing surface moves slower due to viscosity. Okay, because viscosity is high near the surface, near the skin of the hydro wing. And this is especially when the wing crosses a region with high liquid pressure, like perhaps cooler water, or when the velocity is very low. So if the fluid is moving very slowly, like in low power engine / propeller configurations and hence lower water speeds, adverse pressure can pluck the boundary layer away from the hydro wing, leading to a flow separation. So the boundary layer separates from the hydro wing, and it has dire consequences at times for airplanes more than for hydrodynamic vehicles. What are these flow separation consequences for an instance for a water submersible? First, you have a loss of the lift force. Lift performance deteriorates. Stall, one of the common consequences, usually more common for airplanes, but stall is when the wing no longer can generate lift. Okay, loss of lift on the wing. And stall, however, may still happen for water vehicles due to flow separation. This is when adverse pressure gradients overcome viscosity of water near the upper skin of the wing, and it peels off the boundary layer. Second, large wakes forming. A wake refers to a turbulent rotational flow, increasing drag around the wings. That would be the third consequence, which is increased drag due to turbulence, and also formation of pressure cavities. So you have a large difference between pressures in different points. So you have like these air bubbles that form. They can lead to damaging the blades for a propeller. Why? Because you have on one side a high pressure from the water, on the other side where you have the formation of these bubbles, a low pressure. Okay, so they can press against a blade and even break it. So it can be damaging, or it may lead to erosion of the blades. Going back to head pressure, which is, the equivalent of pressure in height terms. What are the major and minor head losses? In fluid mechanics, head loss represents the loss of mechanical energy or pressure head due to friction, disturbances as a fluid flows through pipe systems, interconnected with different widths and curved connections and fittings, correct? So the total head loss is equal to major head plus minor head. Major head. Major head is the loss due to friction. It is the loss of head or pressure caused by the friction between the liquid and the internal skin surface of the pipe over a length L, given by Darcy-Weisbach equation. So HF, or friction head, major head also, is equal to F, which is the friction factor, times L divided by D. D is the parameter, the diameter of the pipe, L being the length, times V squared over 2G. Of course, V is the velocity squared, divided by 2G. G is the gravitational acceleration, which is 9.81 meter per second square. As for F, it is the Darcy friction factor, dimensionless factor. It depends on Reynolds number and the relative roughness of the pipe from the inside, of course, taken from the Moody chart or empirical equations. For minor head loss, also called a local loss, it is the loss caused by fittings, bends, valves, expansions, and other factors that cause flow disturbance, and of course a change of its parameters. HM, or minor head, is equal to K times V squared divided by 2G. K is the loss coefficient depending on fitting type. So for a 90-degree elbow, K is equal to 0.3, actually between 0.3 and 1.5. A sudden contraction, sudden narrowing of the width of the pipe gives you a K value of 0.4 to 0.9. Sudden contraction 1.0, fully open valve gate 0.2, global valve open 10, and T, flow through a branch, gives you a value of 1.8. So as we see, both of the losses are proportional to V square. They are multiplied with V square divided by 2G. Let's do an exercise. So you have a 20-meter pipe with a diameter of 0.1 meters. It carries water at 2 meters per second with 2 elbows, each elbow having a K of 0.75, a valve having a K of 0.5, and its head loss factor F, small f, is 0.02. So let's calculate its total head loss. Okay, so major or friction loss, HF, is equal F times L divided by D times V squared over 2G. Which is 0.02, which is, of course, the loss factor, 0.02 times 20-meter pipe, so L is 20, divided by 0.1 meter, the diameter of the pipe, times 2 squared, the velocity squared, 2 meter per second squared, divided by 2 times 9.81, or the gravitational acceleration value on Earth, is equal to 0.8155. Minor loss, HM, H minor, is equal to K times V squared over 2G. Now K, we have multiple fittings. So you have 2 fittings that are 2 elbows and 1 which is a valve. So you multiply V squared divided by 2G with 2KE plus KV, okay? Or in other words, is V squared divided by 2G times 2 factors of the elbows, 90-degree elbows, plus V squared divided by 2G KV. Okay, so we multiply V squared divided by 2G. It is a common factor for all of these values, these loss value parameters, which are 2 KEs because we have 2 elbows, plus KV, we have 1 valve. So equal to 2 times 0.75 for the elbows plus 0.5 because we have 1 valve having a K coefficient of 0.5 times V squared divided by 2G. V is the velocity at 2 meters per second, squared divided by 2 times G, 2 times the gravitational acceleration. It gives you a value of 0.4077. So the total head loss, HL, is equal HF of friction plus H minor is equal to 0.155 plus 0.4077, or 1.2232. Series pipe systems or serial pipe systems. What are they? These are pipes connected one end after the other end, one after the other, okay, end to end. The flow rate Q is constant in such case. So the head loss is the sum of all the head losses throughout all sections. HL is equal HL1 plus HL2 plus all the HLs, all the head losses, okay, summed up together. In other words, the formula is HL equal the sum between I and N. N is the number of sections, times Fi, which is the friction factor, times the Li, length for each pipe, of course, divided by the diameter of each pipe, each connection, times Vi square again for each section of pipes divided by 2G. As for a parallel pipe, now a parallel pipe is different. Here you have a flow that it divides, or it is divided into two or more branches. So the flow, the original flow, is broken down into multiple flows. The overall flow, the total flow, is equal to the sum of all flows going through the different pipe systems that are parallel. Similar concept, by the way, in electricity, okay? It is the current being broken down or distributed into multiple wires. The head loss in such case is equal for each pass. All the head losses are equal for the sections where the water is being divided. At a junction, mass is conserved. Okay, we have the continuity principle. So sigma Qn, the flow rate at the input side, is equal to the flow rate at the output side. Now for Hardy cross method, Q, which is flow rate, you have R, resistance coefficient, N is the flow exponent, HL is equal RQN. R, which is the flow resistance or resistance coefficient, times Qn, or the flow rate. Delta Q, which is the differential of the flow rate, is equal to minus sigma head loss divided by N, divided, of course, again, you have N is the flow exponent, over the sum of all resistance coefficients, also divided by N, where R, the resistance coefficient, is equal to 8 FL, L again is the length of the pipe, divided by pi squared times G, which is the gravitational acceleration, times the diameter to the power of 5. Now let's talk about pumps and turbines. So in this picture you have a turbine called a Pelton's turbine. This is some form of turbine that generates a mechanical energy by extracting the energy of a jet flow, a jet stream of water going through these bucket-like blades, and these blades would turn because of the water motion, generating a mechanical energy that can of course be transformed into an electrical energy. So this can work as an electrical generator. Let's start with pumps. What is a pump actually? What is the definition of a pump? A pump is a mechanical device that adds energy to a fluid to move it from one location to another, usually from a high pressure point, which is a low altitude, to a low pressure point or high altitude location. There are two typical types of pumps. You have positive displacement pump, which traps a fixed volume of a fluid and forces it through an outlet, such as piston pumps within cars, suitable for high pressure systems having a low flow, low quantity to displace from one location to another. The second type of pumps is the dynamic pump, which works using the centrifugal force. How it works is that it transfers energy to the fluid by accelerating the fluid throughout a rotating impeller, which gives it a centrifugal force, pushing it outwardly. So it is suitable for larger flows and low pressure transfers such as irrigation systems. Okay, so they gain the fluid a centrifugal force, and thus the fluid gains momentum and it moves this way. This is how it works versus the positive displacement pump. The equation of a pump. At first, let's talk about the total head. Total head or total head pressure is equal to the static head pressure plus h velocity plus h friction. Pump power expressed in watt is equal to rho g qh, where rho is the density, fluid density in kilograms per meter cubed, times g, which is the gravitational acceleration, or 9.81 meters per second, times q, or flow rate in meter cube per second, times h, which is the total dynamic head that we've seen in the first line. Now we need to note something, that the power of the shaft is equal to epta times the power of input. It means that the power of water exiting the shaft is not actually the input because you have losses, okay? So eta is the pump efficiency, usually between 60 to 90%. So although the power at the input would be high, the power at the shaft, at the end, the first exit, so to speak, the first opening, is equal to 60 to 90% the power at the input due to losses. Turbine. A turbine is the reverse device of a pump. While pump transfers energy to a fluid to increase its pressure, forcing it to move, turbines extract the energy of a flowing liquid to convert it to a mechanical energy, usually also to electrical power. This is usually used to generate electricity, okay, like hydropower, steam cycles, etc. Types of turbines: impulse turbine, which is the first type that is indicated by the way within this picture, like bucket-like turbine for Pelton wheel, also this is called. So it induces rotation through the fluid hitting the turbine blades, and it transfers momentum through that, okay, like the Pelton wheel. So the fluid hits the turbine blades, inducing rotation and transferring momentum. The second type is the reaction turbines, where the fluid passes through the blade, both pressure and velocity change. In the first type, you have a static pressure and the velocity and pressure do not change. Okay, actually the pressure rather, so it is an external system. The Pelton wheel is outside of the fluid. The fluid is hitting the Pelton wheel. Meanwhile, for reaction turbines, the fluid passes through the blade, both pressure and velocity change. Static pressure increases and the velocity slows down. In such case, blades are immersed fully within the fluid, like water. As an example, Francis and Kaplan turbines. In this picture, we see illustrations of both Kaplan. This is a Kaplan turbine. You see the water as it flows through this turbine, it turns it over, generating power. And this is Kaplan. This is actually Francis turbine, where you have both velocity and pressure are changing, okay, to rotate the blade. So not only impulse works here, but also the velocity of the fluid that would be pressurized. So this pressurization or this narrowing of the tube increases the dynamic pressure of the fluid, inducing or causing the blades to rotate at very high speed. It's very effective, by the way. Francis turbine is a very effective engineering feat. Let's talk about the differences between Pelton, Francis, and Kaplan turbines. At first, in Pelton turbine, rotation is generated by pure impulse force of water jets dropping on the bucket-like blades, turning them and driving the rotation of these blades. The main or the driving energy is actually kinetic. As for Kaplan turbine, on the other hand, is immersed in the liquid and the rotation power is generated through the differential of pressure from up to down. The blades react to that pressure difference from a wider to a more constricted flow, which turn these turbines. As the liquid accelerates due to a narrower tube, it rotates the blades, producing energy. As for the Francis turbine, power is generated via both impulsive and reactive forces. The impulsive is actually the impact of the fluid against the turbine, and the reactive forces are due to the change of the dynamic pressure, as we mentioned. As you narrow down the tube, the dynamic pressure increases because of the increase of velocity when the water is being constricted to a narrower width pipe, which makes the blades rotate at a very high speed. So as the liquid is channeled toward the blade system, its duct is constricted to accelerate its velocity so that it hits the blades with a higher kinetic energy and causes them to turn with a very high efficiency and high speed, producing, of course, an effective power. As for the hydraulic power being extracted from the turbine, it has the same formula for pumps, which is P equal rho G QH. Notice that it is the same as power generated by a pump, except the pump transfers the power to the liquid or the fluid, but turbines extracts that power. However, in both cases, the formula is the same, where P equal rho GQH, rho being the density, G the acceleration of gravity, times Q, which is the flow rate in meter cube per second, times H, which is the head pressure. Okay, now the turbine efficiency eta is equal to P shaft divided by rho GHQ. In other words, the rho GHQ, which is the input power generated from the rotation of the turbine, okay, it should be multiplied by the eta, which is the efficiency factor, to get the power at the exit of the shaft, the actual power being generated. In other words, there is a loss of energy within the mechanism of the turbine, okay, determined by eta. It is the same concept concerning, you know, the pumps, but again, the difference is that the pump gives energy. Here we are extracting energy from the turbine to turn it into a mechanical energy and then into an electrical power. Euler's turbine equation used in reaction turbines to analyze velocity components is P equal rho Q times U1 VU1 minus U2 VU2. Vu is the tangential velocity. You see, there's a differential of velocity between the input or the ingress and the outgress, or the incoming flow and the outgoing flow that is exiting the system after turning the turbine. And U is the blade velocity. Okay, so this is the power being generated by a reactive turbine or reaction turbine, such as Kaplan and Francis turbine. Also, another factor which is used to compare turbine types by quantifying performance is the actual NS value, or the rotation speed NS as a comparison. So for NS concerning Pelton turbine, you have NS equal 10 to 35. For Francis 60 to 300. For Kaplan design above 300. NS is equal to N square root P, which is the power in watts, divided by the head pressure to the power of 5 divided by 4, where N is the rotational speed in RPM and P in watts, the power. Let's do an exercise for turbines and pumps. Actually, this is an example for a turbine. The flow rate Q is equal to 2.5 meter cube per second for a specific turbine. The net head, which is the head pressure, total head pressure, is equal to 30 meters, the equivalency of the pressure. Efficiency is 85% or 0.85. Water density for water, of course, is 1000 kilograms per meter cube for water at the temperature of 20 degrees. Let's calculate the hydraulic power. So the power of the fluid is equal to rho GHQ, equal 1000 times 9.81 times 30, of course 9.81 is the gravitational acceleration, needless to say, times the net head 30 meters times Q, which is the flow rate 2.5 meter cube per second, equal 735,750. Now, this is not the effective power being produced. The power at the shaft is equal to the power of the fluid times eta, or the efficiency factor of the turbine, which is 85%. So it's equal to the power value that we've gotten here in this answer times 0.85, or 735,750 times 85% is equal to 625 kilowatts, around that value, or 625,387 watt. Open channel flow. Let's talk about the characteristics and different features and even equations of open channels. As you see, an open channel is water flowing through a canal where you don't have a closed pipe, for example. The water itself is exposed to atmospheric pressure and it's flowing freely, usually through gravity instead of a driving force that is energetic or electrical, such as in the example of pumps. What is open channel flow again? Open channel flow technically refers to the movement of a liquid with a free uncovered surface which is not pressurized, unlike a pipe flow, like rivers, canals, drains, and irrigation systems. It is exposed to atmospheric pressure and the driving force is gravity, not electrical power, not mechanical. The types of flow in such systems are steady versus unsteady, where the depth and velocity change with time in unsteady flows, and uniform versus non-uniform, which means that the flow depth and velocity of the liquid change along the channel in non-uniform regimes but remain constant in uniform ones. So mainly in uniform versus non-uniform, you have the flow depth and velocity are changing for the liquid, which is mainly the flow depth or the depth of the canal, the wetted part of the canal. Another main characteristic of an open channel is the type of the flow, so to speak, which is divided into three types. The first is subcritical, critical, and supercritical. Now, subcritical, in short, is when the flow is very slow. It's almost not even happening, okay? Critical, it gives you the minimum specific energy for a flow to occur, for a liquid to be flowing, and supercritical would be flowing very fast, meaning that the velocity of the fluid is super high in relationship to the depth of the water or the fluid that we're talking about. As an example, a shallow river that is highly slanted, it has a high slope where the water is flowing very fast, and of course in such case the water would be very turbulent. These are based on a metric called Froude number, okay, and they determine the velocity ratio of the flow versus the depth of water. What is the formula for the Froude's number, which is very important to determine the type of the flow, whether it is subcritical, critical, and supercritical? So Froude's number is equal to velocity in meters per second minus 1, which is the velocity, divided by the square root of the gravitational acceleration times d, which is the depth of water. Now the depth itself is equal to the cross-sectional area of the channel, okay, divided by t, which is the top width of the water surface, okay, or the width of the water within the channel from bank to bank, from the first bank to the left to the second river bank, if we're talking about a river. G, of course, is the gravitational acceleration, is equal to 9.81 meters per second square. Okay, now based on Froude's number, we can determine the flow type. For example, subcritical is where the Froude's number is less than 1. In other words, when the velocity is overcome by the depth and the gravity, okay? So the river or the channel, whatever it is, it would be moving slower, it would have a higher depth in relation to velocity, and it is gravity dominated. As for the critical, Froude's number would be 1, which gives you the minimum specific energy for a flow. And finally, supercritical, Froude's number would be greater than 1. In other words, if you look at the equation, the velocity would be much higher than the gravity times depth, square root, of course. Okay, so it would give you a profile of a fast and shallow flow, okay, which is inertia dominated, meaning that the flow is very fast and it is shallow with a very low depth. Other parameters are the depth, which is the depth of water within the channel, velocity v, cross-sectional area A, which is the cross-section of the river or the channel, wetted perimeter. Wetted perimeter is actually the length of the river bank section under water. So in other words, let's say that this is the actual river and this is the area or the surface of the water, correct? And that's the area of the river bank where you have water, all that area underneath where you have these dots They should have been another color than red, but anyway, so the wetted perimeter P is actually the distance from here to here. That's the upper surface of water added to this area beneath, which is, plunged or wetted by water, not the area, the length of this curve underwater for this section of the riverbank or the channel. So the length is this one, okay, this wetted zone, this wetted line of the section of the river plus this water surface. That would give you P, or the length of the riverbank section underwater. Plus you have hydraulic radius R equal A divided by P, which is the cross-sectional area divided by this wetted perimeter, and energy slope, which is the slope of the river. So let's say this is the river, okay, you have a very high slope here where the water would be flowing very fast. Flow resistance also, which is subject to boundary roughness and shape, another parameter. Boundary roughness means it depends on the type of material within the channel and the shape. So whether it is triangular, circular, trapezoidal, actually that's the channel geometry. Here we're talking more about the shape of barriers. Okay, they both play a role in the flow. And the channel geometry, where you might have a triangular channel like this one, okay, usually for, I don't know, for irrigation or something. You have the circular usually for sewage, trapezoidal for channeling water, and rectangular. Specific energy. This is a concept in open channel flow that helps relate flow depth, velocity, and energy together in one equation, which is critical to classify flow types and design a channel. Okay, this is usually used for the purpose of deciding how to design a channel. Specific energy E is the energy per unit weight of water measured relatively to channel bottom at a given cross section. So E equal Y plus V square over 2G, where Y is the flow depth. V, of course, or V square is the square root of the flow velocity, not root, actually the square of the velocity, divided by 2G, or 2 times the acceleration of gravity. Another parameter is critical depth. Yn or Yc is the designation. Critical depth is the flow depth at which the specific energy is minimum for a given discharge. All right, discharge means when the water is being discharged, is being pushed out, or like thrown out of the end of a duct. That is the discharge. At this depth, Proud number Fr is equal to 1. Okay, and the flow is the most efficient. All right, so this is where you have the most efficient flow. So for a flow rate Q and a channel width B, the critical depth Yc is given by Yc is equal to Q square, which is the flow rate in meter cubes per second, divided by G times B square. B again is the channel width, and together to the power of 1/3. So the minimum energy also is E minimum is equal to 3/2 Yc, which is, again, Yc is actually the critical depth. So the critical depth, in other words, is the actual depth where you have the most optimal performance for a flow. Uniform flow is a flow in which the depth, velocity, and cross-sectional area are constant along the length of a channel. So you have a constant velocity, depth, and cross-sectional area. This is what characterizes a uniform flow. For example, a rectangular water draining channel. The flow is steady and the channel slope is equal to the energy grade line and equal to the slope of water surface. Okay, so there are no jumps or transitions within the flow when it comes to the velocity or depth, or and the flow is stable. okay? So this type of flow is governed by Manning's equation, which we will see in the next slide. Manning's equation is a formula used to estimate the velocity and the flow rate of water in open channels. It actually can be used, of course, for other types of fluids, but usually in general, it is more used for water, such as rivers and ditches, okay, for open channels. V, the velocity, is equal to 1 divided by n, where n is the Manning's roughness coefficient, depending on the channel material, multiplied by r to the power of 2/3, where r is the hydraulic radius. Again, it is equal to a divided by p, where a is the cross-sectional area of the water and p is the length of the boundary of the river in contact with water. So it is the wetted perimeter, or that's the length of the surface of water within the river, for example, plus the wetted curve underneath the water of that cross-section of the river. This is what P is. And R, the hydraulic radius, is A, which is the cross-sectional area, the entire cross-sectional area, divided by the wetted perimeter. S is the slope of descent, for example, the riverbed slope. So the velocity V is equal to 1 divided by N. N again is a Manning's roughness coefficient, depending on channel material, multiplied by R to the power of 2/3, multiplied by S to the power of 1/2, which is the square root of S. Again, S is the slope of descent. Now we can find the discharge flow rate using that equation. Discharge flow rate is equal to A times V, okay? Like the linear momentum, the continuity equation, when we've seen it before, okay? So it is actually rho times V. That's the same concept, okay? M is equal rho times V. But actually that's, yeah, here you have A, the area, okay, instead of the volume, and V is the velocity. So Q is equal to A, cross-sectional area, in meters squared, times V, which is 1 over N R to the power of 2/3 times S to the power of 1/2. Okay, A times V, just like in continuity law. So again, Manning's equation is a formula used to estimate the velocity and flow rate of water in open channels. Velocity again is equal to 1 over N R to the power of 2/3, S to the power of 1/2, and Q, the discharge or flow rate, is equal to A, which is the cross-sectional area, times V, V being this value, this formula here. Now, the typical Manning or Manning's N values are depending again on channel structure. So for smooth concrete, you have 0.012 to 0.017. For earth, a clean and straight soil of the earth, it is 0.02 to 0.03. Rock, 0.035 to 0.05. And vegetation is, the value would be between 0.07 to 0.150, okay, because vegetation, stifles the velocity. You see, velocity is inversely proportional to N. So for higher values of N, or for rougher and more complex channels where you have a higher roughness, higher amount of obstacles, you would have a lower velocity. Gradually varied flow. Gradually varied flow, or GVF, is a flow where the depth changes gradually along the length. This flow is non-uniform, so the depth varies due to changes in slope. Actually, this is usually on intention, okay? This is usually made on purpose in order to slow down a flow, okay? Like when at the end of a duct, when the duct would throw the water within a basin. This is one of the applications. This flow is non-uniform. Depth varies due to changes in slope, changing the cross-section and the presence of obstacles, okay? It can also occur by nature. So governed by the following differential equation, dy over dx, y is the flow depth. So the change of depths through a distance, dx or delta x, is equal to S0 minus SF, which is the difference of the slope from the first point to the second point, divided by 1 minus FR square. FR, of course, is the Froude's number. So you have, again, dy over dx, or the change of flow depths in relationship to the change of distance, or for a specific distance, is equal to the original bed slope minus the seabed slope that is rough, or the riverbed slope that is rougher, okay, divided by 1 minus Froude's number square. Comparison between uniform versus non-uniform flows. So for a uniform flow, when it comes to depths, the depth is constant, but for gradually varied flows, you have a varied depth. It varies slowly, okay? We will call it GVF, the gradually varied flow from now on. As for the flow type, for uniform, it is steady and uniform. For GVH or GVF, it is steady but non-uniform. All right, there's a change of depth, change of steady, it's continuous. This is what steady means, but it's non-uniform. The depth and velocity changes. Governing equation for the uniform flow is Manning's equation, but for GVF, you have the differential equation we showed before. Uniform flow occurs in long straight channels, but for GVF, they occur near transitions and control points, like near a dam. For surface slope, the surface slope for uniform flow is always equal to the bed slope. It doesn't change, but it varies for GVF. Now, the flow is uniform, but it changes for GVF gradually. The depth is constant for uniform, but it changes for GVF. Flow type steady. Okay, that's the same thing. Okay, actually, yeah, these have been repeated twice. I'm sorry for that. Hydraulic jump. So what is a hydraulic jump? Here the title is Hydraulic Jump and Flow Transition. A hydraulic jump is a sudden transition from a supercritical flow, high velocity fast flow with low depths, to subcritical flow where you have a low velocity with high depths. From one type of flow to another in general, not only from supercritical to subcritical. But here the important thing is that you started to notice what supercritical means. For supercritical, you have a high velocity, but a shallow depth. For the subcritical, you have a higher depth, deeper water, but low velocity flow. Okay, it has to do with the layers being, apart from each other. So you have the viscosity on the depths. The boundary on the depths is a little bit far from the surface. This is what makes it flow a little bit slower. And so this transition is accompanied by a rapid increase in water depths and a loss of energy, which is the purpose. So when you transition from high velocity low depths to a higher depths, okay, and low velocity, this is accompanied by a rapid increase in water depths, but also an energy loss. One way it happens is when flowing channel, water needs to be stored in a reservoir. So this is what you would do on purpose. The governing equation is from the conservation of momentum concept for a rectangular channel. Y2, which is the next subcritical depth is equal to 1/2 Y1, which is the initial depth when the water flow was supercritical, times square root of 1 plus 8 FR1 square minus 1, where FR1 is actually the Froude's number before the jump. Again, as a reminder, Froude's number is equal to V, here in this case it is equal to V1, which is the original initial velocity before the transition, before the jump, divided by GY1. Also, Y1 is the initial supercritical depths. In a hydraulic jump, a significant energy is lost after the sudden change of depths due to turbulence, which is a sudden disruption of laminar flow, heat, and locally formed swirls, also called eddies, swirls of water. So this turbulence would lose you a lot of energy because, you know, the streamlines of the flow have been broken. So the same momentum that was pushing the water forward is now partially rotating around a central axis, forming these swirls. This is one way the energy is lost. So again, this is induced on purpose in dam spillways and channels to dissipate the energy to protect the channels from scraping, from erosion due to high forces of drag, also against the bottom and side barriers so that it won't scrape it away. It won't erode it. Delta E is equal E1 minus E2, which is equal to Y2, okay, the second depths, next depths, minus Y1, or the initial supercritical depths to the power of 3, divided by 4 times Y1 times Y2. Flow transition. Flow transition refers to a change in the flow regime from one type to another, like from subcritical to supercritical. We just addressed that moments ago. So let's list the types of these transitions. The first one is subcritical to supercritical, occurs when the flow passes through a control such as a channel contraction, narrower channel, and a sluice gate. The flow grows faster, not because of the narrowing, but basically, you know, you have the depth becomes shallower. You have a control where you have a transition or a change from subcritical to supercritical. The water starts flowing faster, depending on the parameters referred to in the equations before, like the Manning's equation, for instance. Supercritical to subcritical. This occurs naturally or by design, either at the end of the river as it washes into a lake, or in a dissipation channel to slow down the water flow. It often results in a hydraulic jump. Of course, that jump, as we mentioned, would slow down the water. And the critical flow occurs when the flow is exactly at the critical conditions, so Froude's number is equal to 1, which is the minimum energy required for the flow to take place. Usually it's ideal. Why? Because let's say we are talking about a sedimentation transfer from one place to another. Let's say a sewage system. You see, a supercritical regime would make the water flow much faster, that it would leave the sedimentation behind. Okay, so they would be stuck at the bottom of the channel. On the other hand, the subcritical regime would make the water so slow that it won't actually move. Okay, so also the sewer would be stuck, it won't flow correctly. That's why you would need in such case a critical flow in the sewage system so as to transfer the sedimentation effectively to the other endpoint, like throwing it into the sea. At the end, since you stuck so far with me in the video, would like to share with you some references of water and flow, even in the Bible, in the scripture. So, the first one is, "He who believes in me," says Jesus, "as the scripture has said, out of his belly shall flow rivers of living water." That's John 7:38. "When you go through the deep waters, I will be with you." Isaiah 43:2. "They will neither hunger nor thirst, nor will the desert heat of the sun beat down on them. He who has compassion on them will guide them and lead them beside springs of water." Isaiah 49:10. "The Lord will guide you always. He will satisfy your needs in a sun-scorched land and will strengthen your frame. You will be like a well-watered garden, like a spring whose waters never fail." That's supposedly a continuous flow. Correct? In Isaiah 58:11. And here, this one is interesting. "Out of his belly shall flow rivers of living water." It is a flow. It is a real water. It's a real living water here. So, okay. God bless you. Thank you for watching and see you next